Ingo TEWS have performed his PhD thesis at the Technische Universität Darmstadt under the supervision of Achim Schwenk. He defended his PhD in 2015 on quantum Monte Carlo calculation with chiral effective field theory interactions. So after that, he went to INT Seattle in 2015 until 2018 for a postdoctoral position and worked with many people like Sanjay Reddy, Jim Latimer, Joe Carlson, and so on. And then since 2018, he's in Los Alamos, and first as a postdoc and now as a staff scientist. So looking at his impressive list of publications, so it's clear that Ingo is working on many aspects of nuclear physics, and especially related to dense matter physics. So he's an expert in strongly interacting many-body systems, in chiral EFT and nuclear forces, in neutron-rich matter, nuclear astrophysics, neutron stars, and binary neutron-star mergers. He also got many awards. Among them, there is the John von Neumann Excellent Project Awards, and also he obtained a dissertation prize, and recently he obtained the John Heller Prize in Los Alamos National Laboratories. So it's really a great pleasure that you accepted our invitation to give us a webinar in our RESANET bi-monthly colloquium. And now, after this introduction, it's time to let you start. So thank you very much, Ingo.
Okay, thank you very much, Jerome, for this very kind introduction. And thank you very much for inviting me and welcoming me to give a talk to you. I want to talk about nuclear physics and how we can connect it to neutron stars and observations, especially multi-messenger observations of neutron stars. So let's begin. I want to start with a quick recap of neutron stars for those of you who are maybe not too familiar with them. So we know that neutron stars are remnants of core collapse supernovae, so supernovae of stars between 10 to 20 times the mass of our sun. And then the remnant, the neutron star that remains after this explosion, typically has masses of 1.4 times the mass of our sun. But this mass is compressed into a sphere with a radius of only about 10 kilometers, maybe 10 to 15 or something like this. And it happens because stars exist in binary systems, that also neutron stars can exist in binary systems. And here you see basically a picture of two such neutron stars in a binary system. And what happens if neutron stars are in a binary, they can circle around each other. And because they are such extreme compact objects, they will emit gravitational waves, which you can see here. And because of this emission, the system loses energy, the neutron stars become closer, they rotate even faster around each other, emit more and more gravitational waves. And this process goes on and on until the neutron stars finally touch and basically crash into each other in a gigantic explosion, which is called a kilonova explosion, and which basically emits light in a multitude of wavelengths over the full electromagnetic spectrum. And now you can say, of course, this is a very nice video, but of course it's an animation. Do we really see this? And yes, what you see here was really observed in 2017 by the LIGO-Virgo collaboration. And it was not only observed by LIGO and Virgo, it was also observed by about 70 telescopes that exist on the Earth and in space. So it's one of the most observed events, this neutron star merger that we saw in 2017. And these events are really extreme because neutron stars, as I said, are already very dense, but if two neutron stars collide, you really make the most extreme forms of matter that exist in the universe. So before I tell you more about this, I want to give you a little bit an introduction into individual neutron stars and about the history of neutron stars. So as I said already, neutron stars are extreme because they explore these extremely high densities. For instance, if you took a cube of iron with a length of 1 centimeter, weighs roughly 8 grams. If you want to bring it to the densities that exist in a neutron star, you have to compress it to the size of a bacterium, and maybe even a little bit smaller, while keeping the mass constant, of course, to reach these extreme densities in a neutron star. But neutron stars also have extreme magnetic fields. So here you can see a sketch of neutron stars, and in blue, the magnetic field is basically indicated. And the surface magnetic fields can be up to 10 to the 15 Gauss, so really extreme. Neutron stars can have extreme spin frequencies. The fastest neutron stars we know have a spin frequency of only a few milliseconds, or a spin period, or frequency of around 700 Hertz. So it's really an extreme stellar object that we can study, and it is such an interesting stellar object because none of these conditions can be realized in any terrestrial experiment. So as you can see, neutron stars have this onion-like structure. There's an atmosphere, there's an outer crust, an inner crust, and if you go inside the neutron star, there's a core. And to understand these different layers of the neutron star, different types of physics need to be understood. So for instance, to model the atmosphere, one needs to understand atomic and plasma physics. The crust requires understanding in solid state physics and superfluidity. And then in the core, it becomes really interesting for nuclear physicists because the core is really determined by the interactions in strongly interacting matter, mainly neutrons and protons in the outer core. But then if we go to the inner core, there may even be exotic phases like phase transitions to free quark matter. And so neutron stars are really an exciting playground for theorists to play around and test their theories and make predictions for these extreme objects. But of course, these theories need to withstand the test of observation, right? We can observe neutron stars, and I will talk about this later during my talk. And these observations, of course, allow us to really throw out the bad theories and learn about the true theory, right? The true equation of state, or the true properties of the neutron star. And the history of neutron stars is actually quite interesting. It's a rather young field, right? It's only 90 years old. And the history of the neutron star begins clearly with the discovery of the neutron by Chadwick in 1932. And only 2 years later, there was a very, let's say, visionary proposal by 2 astronomers, Walter Baade and Fritz Zwicky. And they had a paper. They gave a talk in 1933 and wrote a paper in 1934. And I give you here like a screenshot from this paper. And they in 1934, because before any neutron star was ever discovered, they stated that with all reserve, we advanced the view that a supernova represents the transition of an ordinary star into a neutron star consisting mainly of neutrons. Such a star may possess a very small radius and extremely high densities. And then a little bit later, a neutron star would therefore represent the most stable configuration of matter as such. Matter as such is dense nuclear matter. And of course, now we know that all of this is true, but back in the days, this was really like a visionary statement, right? And because they had no information to base this on except theory. So so basically the history of neutron stars begins in 1934 with this proposal. And then a few years later, clearly I'm from Los Alamos, so I have to show a picture of Robert Oppenheimer, who was not only the father of the atomic bomb, but he also worked in nuclear theory, and he was also interested in the problem of dense matter. So together with his colleague George Volkoff and with Richard Tolman, he basically calculated for the first time the properties of a neutron star, and he based his treatment of the neutron star on what we know about white dwarfs, right? So he assumed that the neutron star consists of a cold degenerate neutron gas. And then he plugged in this equation of state and found basically that a cold neutron core, there's no static solution for this for core masses greater than 0.7 solar masses. And so they concluded in the end of the paper that it seems unlikely that static neutron cores can play any great part in stellar evolution, which is, of course, from what we know now, it's a wrong statement. But back in the days, this is basically what they found. And this, of course, erased the neutron stars from people's minds for some time, because clearly they found that they would not be important to understand any astrophysical phenomena, because every star that would collapse, every neutron star has a white dwarf-like core of the order of 1.4 solar masses, so neutron stars would never be really made in these processes. But then, almost 30 years later, only then, basically the next important step in neutron star physics was made. Because Jocelyn Bell, together with her advisor Anthony Hewish, they built a radio telescope and they looked out into the space. And in some data that they observed with their radio telescope, they found a signal, a very regular signal, repeating every 1.3 seconds. So here on the right, you can see Jocelyn Bell, and basically here you see a sketch of her nodes. And then you see here that every 1.3 seconds, there was a very regular signal. And in the beginning, they didn't know what it was, of course. So they thought that that one of the possibilities was that they found this was an artificial source of a signal, and this is why Jocelyn Bell apparently called this signal jokingly "Little Green Man 1." But then while she was looking around in other data sets, they found some similar data also from other parts of space. So it was clear that it's not an alien civilization that they discovered, but that it's a rather natural phenomenon. And basically what they found is a pulsar. So a pulsar is a neutron star. You can see this here in the core. And because of the magnetic field configuration, the neutron star basically has these beams of radiation that it emits like a lighthouse. And if by chance the Earth is in the cone of this beam, then we see a regular repeating pulse. And this is what Jocelyn Bell did in 1937. Of course, history is a little bit maybe unfair. So the Nobel Prize for this discovery was only awarded to her advisor, Anthony Hewish. She was not part of the Nobel Prize in 1974 for this discovery. But in 1974, something else happened. There was another very interesting discovery, and this was of the Hulse-Taylor pulsar. So the Hulse-Taylor pulsar is basically the first discovered binary neutron star system. One of these neutron stars is a pulsar with 60 milliseconds spin frequency. And then what Hulse and Taylor found during their observation is that every 7.5 hours or so, the signal time changes a little bit. And basically what that means is, or what they could conclude from this is that's a general relativistic effect. It's called Shapiro delay. So basically, if the two neutron stars surround each other, because of the gravitational bending of light, if the one neutron star is in front of the other, light takes a little bit longer. And this is changing then the frequency of the pulsar pulses, and this is what they could observe. And this is a very famous pulsar because it allows many tests of general relativity, one of which is the prediction of the decrease of the orbital period due to gravitational waves. And here on the right side, you see a plot where the data points are in black and the general relativity prediction is given as a line, and you see this aligns perfectly. So basically, this is why they were awarded the Nobel Prize for their discovery later. But this is basically the first indirect observation of gravitational waves of a neutron star. It's well before their merger, of course, but still, this effect was observed already since the 70s. Then I should mention that in the last decade or so, we discovered 3 2-solar mass neutron stars. So basically, this tells you that there must be something else except the cold degenerate neutron gas that makes neutron stars behave as they behave. And finally, in 2017, there was the discovery I talked about before. It was the first direct discovery of gravitational waves from a neutron star merger. And you see there were the headlines in international news. Here I show you the one from the New York Times from 2017. So basically, only in 2017, maybe 80 to 90 years after the first proposal of a neutron star, were gravitational waves first discovered. And this also basically led to a Nobel Prize for 3 LIGO scientists. Okay, so what stabilizes neutron stars? I told you already about before. There's strongly interacting matter in the neutron star. And if you compare a neutron star with an atomic nucleus, for instance, lead-208, and you use the masses and the radii of these objects to compute the average densities, you see that the density in both systems is pretty similar, around 10 to the 14 grams per cubic centimeters, which is the nuclear saturation density. So although these scales of these two systems are so different, right, they are connected in their properties because they explore the same densities, the same nuclear densities, where strong interactions, nuclear forces become very important. And it's the nuclear force that exerts the pressure that stabilizes the neutron star against gravitational collapse. Okay, so this is also the reason why nuclear physicists are interested to study neutron stars, because the same interactions among the same constituents play a role in the nuclei that we probe in the lab and in the neutron stars that we probe in the cosmos. So if we observe one, like a neutron star in the cosmos, or if we measure a nucleus in the lab, it will already automatically influence our theory for the other domain and vice versa. So I want to talk a little bit about the nuclear interactions that we need to have to understand neutron stars. And then I want to talk about observations and observational constraints that exist and what we can learn about them from them about the neutron stars. Okay, so the main ingredient we need to describe neutron stars is the equation of state. And because neutron stars, basically what we observe about neutron stars, their structure can be basically described in the so-called mass-radius relation. And here you see an example, right, where the mass is just plotted with the corresponding radius of the star. And this is what we can observe with telescopes, let's say. And using the Tolman-Oppenheimer-Volkoff equations, we can basically compute this curve once we have pressure and energy density as input. And since neutron stars, they might be very hot objects, they have 10 to the 7, 10 to the 8 Kelvin temperatures, which sounds very much. But because of these high densities that exist in the neutron star, the thermal energies are very small compared to the typical energies of particles there, the Fermi energy. And so you can assume that the neutron star is a cold object, and then the equation of state is just given as this relation that tells you what is the pressure and the given energy density. And with this, you can then solve the TOV equation. So basically, if you integrate this to a certain density, you get a point in the mass radius curve. And of course, you can do this for many more points and you map out this mass radius curve. And so observationally, you do this and then you can re-infer the equation of state. The problem is that if you look into the literature, there's a very famous plot for the equation of state and for the mass radius curve, given many different equations of state. And what you automatically can see is that there's a huge spread. I mean, the radius of a neutron star varies between 10 and 15 kilometers, and that's almost a 50% uncertainty in the equation of state. So if I now asked you which of these equations of state are good and which ones are bad, you cannot really say this, right? Because none of these lines provides any theoretical uncertainty estimates. None of these are constructed on some fundamental guiding principle. And then you don't know, if I give you a certain equation of state, you don't know how to systematically improve it to make it better and better and reflect nature more and more. And the only thing you can maybe do to rule out some of these equations of state is using astrophysical observations, like for instance, the observations of these two solar mass stars that I said. So for instance, they rule out clearly this, for instance, this equation of state, because the maximum mass in this equation of state is well below this. But even if you enforce a constraint like this, there's still a huge spread. So if we want to, and the reason for the spread is basically that at the densities that are really probed in the neutron star, we don't have much information. We see that at low densities, so here you see a schematic sketch, at low densities, we get information from experiment, and this is why all of these equations of state converge if you go down here to low mass stars with large radii, so to low densities. And then at very high densities, we can learn something about neutron stars from perturbative QCD, which is a way to solve QCD basically. But it's not really important for neutron stars themselves. And everything that happens in between, we cannot, we don't have robust information and no robust theoretical models. And we don't even know what are the degrees of freedom in a neutron star. There could be quarks, there could be only neutrons, there could be other exotic condensates. We don't know this, and this is why there's this huge spread. And this is, by the way, this is what we want to address. So just another brief introduction. If we want to understand the equation of state, so the pressure as a function of energy density, in principle, what we need is the energy per particle of nuclear matter, because the energy per particle together with the baryon density gives us the energy density, and the derivative of the energy per particle gives us the pressure of a neutron star. So if we have the energy per particle as a function of density and also of a function of proton fraction, because in neutron stars, there are not only neutrons, there are also some small residual fraction of protons. So if we have this function, we can describe neutron stars. And this function is actually quite interesting because it connects the physics of neutron stars at very small proton fractions up here, close to pure neutron matter, with the physics in the laboratory, which is basically described by symmetric nuclear matter with an empirical saturation point. Because the symmetric matter is basically what we explore with atomic nuclei. So it connects to laboratory experiments. And the same functional up here at low proton fractions, high energies, connects to astrophysics. And the difference of the two is called the nuclear symmetry energy. And this is also an interesting quantity because it sets the properties in some heavy ion collisions. It is relevant for the size of the neutron skin in heavy nuclei. So basically, the energy per particle of dense matter allows us to bring together many different fields, astrophysics and nuclear physics in the lab. But since I said we need this equation, how do we theoretically compute this equation of state? And I want to focus here on microscopic calculations because this is what I do. And microscopic calculations basically means that we really want to solve the Schrödinger equation. So we need two things. First of all, we need some input that describes the interactions among nucleons, for instance, neutrons that you see here in the sketch. There are two interactions among two neutrons in the neutron star, but because densities are so high, there can be interactions among 3 neutrons, 4 neutrons, and whatnot. And we need to understand these interactions so that we can write down the Hamiltonian, which then is the input for the Schrödinger equation. And then, because it's such a complicated system, we need to have some numerical methods that solve the Schrödinger equation. And there are many different methods on the market. I just name a few here. And I don't want to talk about the methods in great detail. I rather want to focus on chiral effective field theory and what it tells us about the interactions. But if we have both of these ingredients, we can compute the energy per particle. Okay, so what is chiral effective field theory? So we know that an atomic nucleus, for instance, consists of strongly interacting matter, and we know that this strongly interacting matter is described by quantum chromodynamics, which tells us that, for instance, the neutrons and protons in the core of an helium-4 nucleus, they are made out of quarks. So here you see a sketch of this helium-4 atom, actually, but it's of course not to scale. But if you focus on the core, you see that there are these up and down quarks. And if we wanted to solve the system directly on this quark level, it is extremely complicated to do. There are some lattice QCD studies that try to achieve this goal, but it's a very challenging problem. It's computationally very demanding. And so at the moment, of course, you cannot use this lattice QCD to compute the matter in the core of a neutron star. So this doesn't work yet. But chiral EFT basically uses the fact that if we probe this atomic nucleus at lower energies, we don't see the quark substructure. What we see are neutrons and protons instead. So basically, chiral effective field theory is an effective field theory that uses neutron and proton degrees of freedom to describe the strongly interacting matter. And if you use neutron and proton degrees of freedom, typically your potential looks something like this. So you have attraction at larger particle separations, which are shown here along the x-axis. And then if you bring neutrons or protons, nucleons closer and closer together, you see there's this repulsion at short ranges, right? Which is basically what stabilizes the neutron star. And if you look at this curve, it is made up of many different interaction mechanisms. So you can have 2 neutrons and they exchange a pion, for instance. That's the famous 1-pion exchange, which is already known since the 30s. And this is describing the long-range attraction of 2 nucleons. But then if you go to shorter distances, higher densities, there are of course more important, other important contributions, many more contributions. For instance, there's the 2-pion exchange where 2 nucleons exchange 2 pions, as the name suggests. There can be 3-pion exchanges and so on. And at shorter distances, there are basically interactions are modeled by contact interactions, where you just have 2 neutrons having a short range contact interaction. And so chiral effective field theory takes these many different interaction mechanisms and arranges them in a systematic order by order scheme. So you see there's something called leading order, which is the most important contributions to the nuclear interaction. And you see there are these 2 diagrams appearing, right? There's the 1-pion exchange, which is as leading order, and there's some short distance contribution. And then if you go to higher orders, you see that there are more and more diagrams, more and more different interaction mechanisms appearing. And the great thing about chiral effective field theory is that it provides this systematic expansion of nuclear forces in momenta. So this expansion is in powers of momentum over some scale, which is called breakdown scale. And I will talk a little bit about this later. So if you go to higher and higher orders in this expansion, you see that interactions become more involved, but they also help you to lower, to increase the accuracy and lower the uncertainties, or basically increase also the precision of your calculation. And a very important consequence of the systematic scheme is that chiral EFT allows systematic uncertainty estimates, because if you have the systematic expansion and it is converging, then you know that if you, for instance, terminate your calculation at 3rd order, you can estimate the size of the higher order diagrams, and you can use this to get an uncertainty band on your calculation. And also it provides a natural explanation, the natural hierarchy for many body forces like 3-body interactions, 4-body interactions, and so on. Okay, so I just want to show you a quick example. If you focus on these plots, let's say we focus on this one. So these are scattering phase shifts, neutron-proton scattering phase shifts. And in black, you see basically the extraction by the Nijmegen, the Nijmegen partial wave data. And then you see calculations order by order in chiral EFT. And so if you go to higher and higher orders, as you see the uncertainty bands, they decrease, and you agree more and more with experimental, or basically with a phase shift extraction in this case. So you see this very nicely, how this works in all of these different phase shift partial waves. But of course, this also works for nuclear systems. And I will show this to you in a little bit. I just want to stress that this feature to get the uncertainty estimates is extremely important, because any calculation that we do is always limited by our incomplete understanding of the nuclear interaction and our way of how we calculate or solve the Schrödinger equation, for instance. So there are always these limitations. And so if you really want to learn from one system like neutron stars, where you see you have these uncertainties, if you want to learn from to analyze neutron stars and extract reliable information on the interactions that also govern the isotopic chains, let's say magnesium and chlorine that you can see here, which also are covered by uncertainties, only if you have a true estimate of your uncertainties, you can really make this connection properly, right? So it's very important to get these uncertainty estimates in any nuclear system that you study. And I think it's also important to have a consistent approach that can address both nuclei and the matter in neutron stars, so that the same interactions and the same many-body methods can be used to solve these different systems with uncertainties. And then, as I say, you can learn. And microscopic studies that use chiral EFT are ideally suited, because chiral EFT provides you with this uncertainty estimate. But I want to put in a little disclaimer. So I told you that chiral EFT is very powerful, but there are still many open questions. So it's not, it's of course, it's with any theory, right? There's always something more to learn. And with chiral EFT, there are also many questions. So I mentioned this breakdown scale before, which is basically the denominator in this momentum expansion. And we don't really know yet what exactly the breakdown scale is. So the breakdown scale describes when the theory breaks down, as the name suggests, and when new physics has to be taken into account to study a certain system. And there were studies in the last years, here's the most recent one from 2020, that put this breakdown scale somewhere of the order of 500 to 600 MeV in nuclear matter. But we don't know yeah, there's no ab initio way of knowing what the breakdown scale is in a certain system. You have to test it after the fact from the convergence of the series. And there are some other problems that I wanted to mention. For instance, results can depend on the exact way of how you write down your interaction, which is called regularization. And on the scale you choose in this regularization, so the cutoff scale. And there is a dependence on these two, which has to be understood. We need to understand if in which systems and up to which densities, for instance, the series converges, and if there are other effects that maybe hinder the convergence or enhance the convergence. So that's something that needs to be understood. And then in this theory, there are several unknown coefficients that have to be fit to experimental data. And the question is, what is the best way to determine these coefficients? So these are open fields of research. And as I said, there are these open questions and problems, but people work on this. And there's a lot of progress made in the last years. And I want to show you that Chiral EFT works quite well for atomic nuclei before I come to neutron stars. So on the left-hand side, I show you basically this is the ground state energy of the oxygen isotopic chain as a function of mass number. And then black, you see experimental results. And then these different points indicate calculations using different setups, computational setups to calculate this oxygen chain. And you see the computational method itself doesn't really lead to big disagreements, right? So the microscopic methods that people use at the moment, they find very consistent results and they agree very nicely with experimental results. And they also find, for instance, the oxygen drip line at oxygen 24. So this is it's a very nice plot that shows you that you can understand these features. And here as an example, oxygen. And then on the right-hand side, I show you some other calculations of several light nuclei up to oxygen. These are the binding energies and these are the charge radii at different orders in the EFT, and then always compared to experimental number. So here you see this order by order convergence, and it agrees very well with the experimental point, and this happens up to oxygen. So there's an excellent description of nuclei of the medium mass region. I didn't show you plots for heavier systems, but there are calculations for heavier systems, and they agree quite nicely with experimental results. So Chiral EFT really works well for atomic nuclei. But how can we use it for neutron stars? So I show you on the left-hand side the energy per particle that I introduced before as a function of baryon density up to nuclear saturation density. And this is for pure neutron matter. And pure neutron matter is always a great system to study because it's so close to the matter in neutron stars that has a few % of protons. And here you see a few of the equations of state that were on this plot before. And then you see the mass radius curve that results from these model equations of state that are commonly used in astrophysics. So Chiral effective field theory now also provides you some constraint on the neutron matter equation of state. And you see here this in red, this is the uncertainty band coming from the Chiral effective field theory calculation. And you see already this uncertainty band is very nice, right? Because it tells you where the how our knowledge of the equation of state changes with density. And you can already use this calculation in pure neutron matter, for instance, to rule out certain equations of state, like this one, this NL3 one here, which is very, very stiff at nuclear densities, much stiffer than Chiral EFT would predict. The question is, how do we extend this now to the densities explored in a neutron star? Because in the core of a neutron star, densities could be 8 times saturation density, so 8 times as high as the limit in this plot. And of course, one possibility would be to just use these Chiral effective field theory interactions and solve the system at higher and higher densities. So basically, if you zoom a little bit out, so this plot is basically this cut here on the right-hand side panel. If you push this calculation to higher and higher densities, what you see is that the uncertainties increase very, very, very fast. And the reason is that your momentum scale in this momentum expansion approaches the breakdown scale more and more and more. So at some point, the assumption that you only have neutrons and protons and they can only exchange pions, basically in multiple pion exchanges, for instance, this assumption breaks down at some point. And so Chiral EFT tells you about this by giving you larger and larger uncertainties. And you can maybe get rid of parts of this uncertainty band by using some other considerations. But generally speaking, you cannot really take a Chiral effective field theory calculations beyond 2 times nuclear saturation density. This is really the breakdown, the limit of applicability of interactions that are commonly used at the moment. So there needs to be some other way of extending these calculations to the densities that we, for instance, probe in this core of a neutron star. And there are many ways. You can use polytropes, extensions in the speed of sound, meta-model equations of state, or Gaussian processes or other non-parametric inference methods. And I just want to give you a quick sketch of how this works. So you would take your calculation at your low densities where you can actually perform the calculations. And you would, of course, have to bring it into beta equilibrium. So you need to account for the small fraction of protons that is in the neutron star. But then, as I said, at a certain density, your calculation breaks down and you cannot trust it anymore. So beyond that, in such general extension schemes, you don't really want to make any strong assumptions about physics. And for instance, here, I show you a sketch in the speed of sound plane. So we know the speed of sound is larger than 0 because otherwise a neutron star wouldn't be stable. And we know the speed of sound needs to be larger than 1 because otherwise the equation of state wouldn't be causal. And so in such a general extension scheme, you sample basically every equation of state that is allowed within this gray area. So I show you here a few examples, that show you there are many different curves that are possible. But of course, there are infinitely many of these curves, right? And you just sample from this using either polytropes or like these curves in the speed of sound, whatever you want. And then basically by doing this, you extend the systematic uncertainties that you have down here to higher densities because you don't make any additional assumptions, right? The only thing you constrain is that the neutron star is stable and causal, which is a general physics consideration. And if you do this, you can extend this band, for instance, and you would find this result for the mass radius curve. So still this is the true estimate of the uncertainty in the neutron star mass radius relation. If you use this calculation. And you see the uncertainties are still very large, but for instance, as I said, this one equation of state, which has this very high pressure, it leads also to a very large radius, and this is outside of the uncertainty band here. So in principle, based on this, you could say that this equation of state is just too stiff at low densities, and you can rule it out. But as I said, this uncertainty is still pretty large, and now the question is, how can we learn more about the interactions, more about the equation of state? And this is where I want to begin talking about observations. So one of the most precise ways of observing neutron stars is by measuring their masses, because we can measure the masses using pulsars, and the observations using pulsars are all based on timing, and this can be done to a very high precision. And you see here a famous plot by Jim Latimer where he collected many different neutron stars. For instance, here you see the Hulse-Taylor binary that I mentioned in the beginning. But there are many, many, many more neutron stars, as you can see here. And I told you in the beginning, there were 3 neutron stars so far that were observed with masses around 2 solar masses. The first one was observed in 2010. And over the years, the mass went down a little bit from 1.97 to 1.91, roughly, solar masses. Then there's another star that found, or another measurement that found a neutron star of roughly 2 solar masses. And the heaviest neutron star at the moment is around 2.1 solar masses. And as I said in the beginning, these masses are mainly measured using Shapiro delay. So you look at the signal and you see how the signal, signal differs over time depending on the orbital position of the 2 neutron stars. And basically from the signal, you can then estimate the masses of the neutron stars. And this is here the figure from this paper, for instance. So if we use these 3 neutron stars, the 2 solar mass neutron stars, which you can also see in this plot, in this Latimer plot down here, basically it cuts away all this space from the uncertainty of the mass radius curve, because these equations of state do not give you the necessary repulsion to make this 2 solar mass neutron star that we observe in nature. So this is one way of observing neutron stars, but then there has been tremendous progress has been made in the last years, and a huge amount of new data has become available. The first great detection, let's say, of the last 5 years is this observation of the neutron-star merger. And basically what you see here is different figures that all describe the mergers in different wavelengths. So if you start down here, you see the gravitational wave signal as a function of time until merger. And this blue signal is basically the gravitational wave spectrogram that was extracted by LIGO. A few seconds later, there was a gamma ray burst that was detected by gamma ray satellites around Earth. And a few days later, you see here 2 optical pictures, images, one made on August 17, where you see this blue source that dims and becomes more red in the days after. And here you can see also the corresponding spectra. So you really see that this one event was observed by many different telescopes using many different messengers at the same time, and this is what is called multi-messenger observation. So this is one of the events that provided a lot of information on neutron stars, and I will talk about this. The other thing that provides important data is the nicer telescope on board the International Space Station. And here you see a little animation. Actually, that's a video. It's a GIF of a real video. And you see basically the NICER satellite, which is this X-ray telescope. It's on board the International Space Station, and it tracks neutron stars in the sky and measures their X-ray signal. And this can be used to extract also masses and radii. I will talk about this in a little while. So we can learn from all of these observations. Let's start with neutron star mergers. So if we have these neutron stars that surround each other, as you can see here, while they are far apart, nothing much happens to them. But you can see in the short, brief time before they are merging, when they are very close, they begin to deform. And this deformation is called tidal, basically can be measured as so-called tidal deformability. So the ability of the neutron star to be tidally deformed under the gravitational wave of its partner. And this tidal deformation is imprinted in the gravitational wave signal. So if the neutron stars are far apart, the gravitational wave signal is very regular and what you would expect for point-like masses. But if the neutron stars are very close, there will be some imprint of this tidal deformability on the gravitational wave signal. And this tidal deformability, which is shown here on the y-axis, correlates very strongly with the radius of a neutron star. Because if you have a very big neutron star, it's very easy to deform this guy. But if you have a small neutron star, it is very compact and it cannot really be, it resists deformation to a larger extent, right? And so for low radius stars, you have a low tidal deformability, while large stars, big fluffy stars, have a huge tidal deformability. And so you can measure this from the gravitational wave signal, and this is basically what LIGO does. And as you know, LIGO is basically an interferometer. And you see here a picture of LIGO in Hanford in Washington State in the US. So basically you have these gigantic 4-kilometer long arms, which you can also see here. And if the gravitational wave passes through these mirrors, they move a little bit and you see a changing interference pattern in your detector. And from this, you can then extract the gravitational wave frequency and also the tidal deformability. And if you have not seen this, it's really a fantastic telescope. So if you ever come to the US and you have the chance to visit LIGO, they are happy to have visitors. And I just encourage you to go there and look at their technology. It's really impressive. Okay, so this is the first thing we can learn from neutron star mergers. We can learn about this tidal deformability. We can also learn something else from neutron star mergers. If you have 2 neutron stars, and let's say a given equation of state. And this equation of state, or the true equation of state in nature, it leads to a low possible maximum mass for neutron stars. Then if 2 neutron stars merge, and the total mass of the system is then much larger than this maximum mass that is supported by the equation of state, you will not really expect anything, any interesting effects to happen except a prompt collapse to a black hole, because the mass is so much larger than what can be supported by the interactions in the remnant after the collision. So you will have this prompt collapse. if instead you had an equation of state that gives you a very large maximum mass, much large, for instance, almost as large as the total mass of the 2 neutron stars, or maybe even larger, you would have a long-lived neutron star. So either a neutron star that collapses after some time, or maybe even a stable neutron star. And if your equation of state is somewhere in between, right, then you will have a combined, or like something in the middle, where you have first a neutron star that lives for a certain time, but then it collapses after, let's say a few hundred milliseconds, maybe a few, maybe up to seconds or so. So based on the maximum mass of the equation of state, the outcome of the neutron star merger changes. Now, we can observe the outcome of the neutron star mergers using electromagnetic radiation. For instance, if you look at this optical curve, you really see that there's some change happening in the neutron star. And you can also see this from the light curves. And if we go back here, depending on these different cases that can happen depending on the maximum mass of the equation of state, you also observe different electromagnetic signals. For the prompt collapse, you would expect to have a red light signal. For the long-living neutron star, you would expect to see something blue. And for this middle case, you would expect to see something blue and red. And this is exactly what you see here. So there are two components to the electromagnetic signal. One is blue, which we observed first. And then there's a red component, which we observed later. And so it is the current belief that the neutron star merger that we observed in 2017 exactly went down this middle road. So the equation of state maximum mass is somewhere in the middle. And so the neutron star collapsed after some time, a few hundred milliseconds. Okay, so what can we learn now from this? The first thing is, what I show you here now is the mass-radius relation. And in blue, you see many different possible equation of state models. And all of these models are constrained at low densities from nuclear theory, from chiral effective field theory calculations that I talked about before. And then in the lower panel, I always show you the distribution of the radii of these neutron stars. So you see for our prior, so for what comes out of Chiral EFT, we chose the equations of state such that the distribution on the radius is rather flat. Okay, and now we bit by bit include observational information on neutron stars. So I told you we have these 3 neutron star observations coming from the 3 pulsars, and you can combine them. Basically, you see these 3 lines. This is like the likelihood, right? The higher you go in mass, the more likely, or the higher the likelihood is for these individual pulsars. And then from what I talked about before, from the remnant classification, so if it's either prompt collapse or a long neutron star or something in between, from this you can extract an upper limit on the neutron star maximum mass, which is given by this red dotted line. So if you combine this, you see that the neutron star mass needs to be somewhere in this, given by this black line. And if you can enforce this, basically this is this purple band, you see that some equations of state are ruled out, mostly these very stiff equations of state up here that give you very large neutron star masses, but also some soft equation of state that give you some low neutron star masses. They are ruled out. And basically in blue, you always see the equations of state that survive the constraint, and in gray, you see the equations of state that basically would be ruled out based on this constraint. And then you see here how the radius changes. Now, there's another observation that I mentioned before, and this is NICER. NICER is the Neutron Star Interior Composition Explorer, and it's a NASA mission on board the International Space Station. And basically, it measures this light bending from the surface of a neutron star. So if you have a small neutron star, there's more light bending, and you observe a different, because the compactness is higher. And if you have a large neutron star, lower compactness, there's less light bending, and you would observe a different signal based on the radius of the neutron star. And this is what NICER measures. And the NICER data has been, there have been 2 independent analyses done by 2 different groups within the NICER collaboration, but they found very consistent results for the masses and radius of neutron stars. And here you see basically the posterior that they find for the mass radius relation for this one neutron star. And these are 2 different models, but you see they are pretty consistent with each other. So statistical uncertainties seem to be under control for this for these observations. And if you put in now NICER, you see this huge ellipse. So uncertainties are still very large. But if you put this in, you see again how the radius changes. NICER pulls the radius up to larger radii a little bit. And softer equations of state are ruled out even further. Okay, so here I just basically moved the NICER plot, the one that I just talked about, to the left. And now in the next step, we include gravitational wave information from this merger, GW 170817. And here you see the posteriors on the two objects. And you see that gravitational waves now, they move the radius again from something of the order of 12.1 kilometers to something 11.7 kilometers. So gravitational waves rather prefer a softer equation of state, a lower radius neutron star. From the electromagnetic signal, you can also extract some additional information, but it doesn't change the radius that much. It mostly changes how the uncertainties look like. So you see a little change down in the posterior here, but you don't really see a shift. So yeah, you get some information out of the kilonova, but not too much. And here again, this is the plot I just talked about. And then the next step, there was a second neutron star merger observed in 2019 in April. This was a neutron star merger that had a very high total mass. So the individual neutron stars are a little bit heavier than the ones before that were observed before. And if you include this information, you see that the radius is changed a little bit, uncertainties are changed a little bit, but it's still a very uncertain event, and it doesn't add too much additional information here. But still, from each of these individual observations, if you bring them together, you really you basically get a consistent picture of the neutron star. And as you see, you can learn a lot, right? You can rule out a lot of information on very stiff and very soft equations of state. And so here I just wanted to summarize this again. So basically, you see how the radii of a typical neutron star changes the more observations you take into account. And of course, this will improve in the next years, because there will be many more observations by LIGO, there will be many more observations by NICER. And so the more data points we have, the lower our uncertainties become, and the more precise information we get on the mean of the neutron star radius. But at the moment, we find something around 11.7 kilometers, plus minus roughly a kilometer uncertainty. And you can also use these observations. This is very interesting. I just want to briefly mention this. You can also use these observations to get information on the distance of this object, and then use this to estimate the Hubble constant. And there's something called Hubble tension, because different measurements of the Hubble constant using either supernovae or the cosmic microwave background, they find different values for the Hubble constant, and they are actually disagreeing with each other, let's say roughly 2 sigma or so. But if you use neutron star merger observations, you can get some estimate on the Hubble constant. And it's still a very large uncertainty, as you can see here. It agrees a little bit better with a cosmic microwave background. It doesn't rule out the other one yet because of the uncertainty. But still, neutron star mergers might also be able to give us some answers to cosmological questions that are currently uncertain. Okay, and with this, I want to summarize. So neutron stars will provide many constraints for nuclear physics. They will tell us about the fundamental interactions that govern strongly interacting matter. We can use their information to talk about how basically nuclear matter organizes itself, which phenomena there exist. And we can learn a lot about astrophysical phenomena and many different astrophysical processes. For instance, nucleosynthesis. I could not address this during my talk, but neutron star mergers basically allow us to extract a lot of information on nucleosynthesis, and they are now thought to be the main site where the rapid neutron capture process takes place. But if we want to address these different, very interesting questions, we really need microscopic studies of neutron-rich systems, matter and nuclei, and we need these studies with uncertainty estimates, and we need to improve these studies to get better and better uncertainties to be able to understand neutron stars more and more. Okay, so here it just is another summary of the results. I think I will just leave this flashed basically just a quick outlook. I just wanted to show you this outlook slide. In the last observing run, So in the second observing run of LIGO, we saw one neutron star merger, and this was the GW 170870, which you see down here. It was the closest merger we observed to date, and it was really lucky that we saw this event. Then in the next observing run that ended 2020, so last year, we had many different candidates for neutron star mergers or neutron star black hole mergers, two of which are also very interesting. One of is this, it's basically this event down here in April, and there's another one in August. But you see, there was no other event that was so close yet as GW 170870. But next year, LIGO will, after some upgrades, take data again. So we can expect this plot to fill more and more and more. There will be many, many, many different new observations made. And they will allow us to hopefully, they will allow us to get a much better understanding of the equation of state. Okay, so with this, I want to thank all my collaborators. And of course, I want to thank the funding agencies. And I want to thank you for your attention. And I will go back to the summary slide in case you have questions. Thank you very much.